So let's start with the definition. I'll refer to decorated graph gamma as something that is basically a graph. So it has sets of vertices and edges such that vertices of gamma are assigned an integer number. So there will be b1, b2, and so on, bi assigned to every vertex. So in other words, for I in what I'll call set of vertices of gamma, will have bi contain in integers. Okay, so there are lots of such graphs, and we can encode the data of this graph. I'll continue with this definition here. In adjacency metrics, I'll call it capital B to be the matrix which has one if vertices I and j form an edge. Then bi if I equals to j, and 0 otherwise. So that's going to be the defining set for some class of models that we'll consider today. We'll enrich it if time permits. But basically, you should think that input data for whatever I'm going to do today, in particular constructs or in log VOAs, will be this input data of a decorated graph. So remark is that yesterday we were talking about three-dimensional n equals 2 theories, and there are 2D 0-2 boundary conditions. So this data can naturally define for us a set of 3D n equals 2 theories. In fact, these are particular example class or large class of theories T of M3 that associated to three manifolds. I may not emphasize the three manifold aspect yet. You can just think of it as a universe of 3D n equals 2 theories which have this large quiver-like structure. I mean, there are infinitely many decorated graphs in the universe, and you can consider say dinking diagrams or whatever you like, and associate to 3D n equals 2 theories. And their natural rule is to say what basic ingredient we associate to vertices of the graph in the context of this theory and to the edges. So there are two basic building blocks for building graph, and therefore there should be two basic building blocks for these theories. And my vertex is decorated, so there is this label B sitting at every vertex. So this is actually easy to state. So this is going to be 3D n equals 2 vector multiplet. Oops, vector multiplet, meaning it's a gauge node, very much like a quiver description. But when we use quivers, we often associate integer which decorates the vertex with the rank of the gauge group or its dimension of the underlying vector space. In this case, here it's not. Here it's something different. And here we're going to use the fact that we're in 3 dimensions. So in 3 dimensions, you can write for gauge field Chern-Simons term. So maybe I should finish this first. Vector multiplet for group which is SU2 for us. Remember, I told you that most of what I'm going to do is for SU2. There is generalization to SUN. Actually, there are lots of generalizations of what I'm going to say, and they're easy and fun to play with, but this is going to be big enough for us to study. Yeah, so to continue, in 3 dimensions, once you have gauge connection, you can write Chern-Simons term, Chern-Simons of A, and in the right, so since we're in 3 dimensions, we can write this, but it has a level, so that should be integer, and that's going to be precisely this integer b that we assign to vertex. So in particular, that's the reason for me to choose this b to be integral. Otherwise, the expression makes no sense. So in other words, what I'm saying is that a vertex in this input data will correspond to 3D n equals 2 gauge multiplet with super Chern-Simons term at level B, okay? Super meaning super symmetrized, because my gauge multiplet has also gluinos or gauginos, whatever you call them, and of course I have to include fermion terms as well. So Chern-Simons term in 3 dimensions gives mass to gauge connection, gauge multiplet, and also mass to the fermions. So this is nice and easy. So in particular, if I have a graph with, I don't know, 100 vertices, it means that I have a gauge group SU2 to 100, okay? I mean, nothing wrong with that. That's slightly bigger than our standard model. So next ingredient in this construction or in this input data is edge, okay? So edge connects 2 vertices. And next, I have to tell you what that is in terms of T of M3, but I actually don't know. So yesterday, I talked about this group valued fields. So that's exactly where it enters. So this is non-Lagrangian. Non-Lagrangian means that at present time, whenever the speaker is telling you about this, Lagrangian is not known. So, but it doesn't mean that some of you may not be able to find some UV theory which flows into strongly coupled point, which is what this is. So there is a chance that you may find Lagrangian description or some RG flow to that. Anyway, at present it is non-Lagrangian, Skirmy-like theory, strongly coupled theory. SCFT. So this theory definitely has to do with maps into you can describe it as a nonlinear sigma model based on group manifolds, which in our case will be SL2C. So that's very typical in the context of this T of M3 theories. And yesterday I explained again why these are interesting theories, why we actually cannot really be naive about them, why we cannot just replace this with linear matter. And origin of this sort of group valued fields was essentially holonomies from high dimensions. So that's how we can think about it. So yesterday I didn't get quite right the reference for this, and some of you were asking me this. I apologize, I didn't get all the authors right, so it did include Stanyuk Park, who is in the audience, and Nikita Sapenko and others, but the easier way to find this paper is 3D module correspondence for mapping tori. So that's what I was referring to last time. And again, some of you asked me this question later. So it gives description the best we know in terms of this Skirmy models and so on. And various people try to find Lagrangian for this theory. I'll give you lots of computations later which produce various indices. So actually, there are lots of checks for you. In other words, if you have a candidate, you can just check. I mean, you can compute its index and see if it gives the right answer. And a person who did a lot of work in this direction is Hee-Jun Chong. So he has not one, but a whole series of papers roughly in the range of from 17 to 19 or maybe even 21, which explore in various degree of complexity possibility of having Lagrangian for this theory. So there are many candidates that people thought would be natural, and all of them turn out to be not quite right. For example, this edge, because it connects two gauge nodes. So we know what vertex is. Vertex is basically gauge field, that's easy. But edge is roughly bifundamental matter, or a matter that should be kind of in fundamental representation for both SU2 on the left and SU2 on the right. So as such, it looks very much like what people sometimes call theory T of G in the context of 3D n equals 4. So that's not correct. And there are lots of other things that people considered, but unfortunately, we still don't know this edge theory. So it's quite mysterious. So therefore, problem for physicists, problem in a sense that it's not a homework, it's not something that I expect to be easy, and something that if you solve, you write a paper about, is to actually find 3D n equals 2 edge theory. Okay, and then all of this class, everything I'm telling you about will be Lagrangian, okay? In any case, this is end of the remark. And my next goal is to do what I promised to do for you, basically compute this Gukov homology or BPS spectrum of such 3D n equals 2 theories with 2D 0, 2 boundary condition, so 2D 0, 2 boundary conditions. So from this, I can get a lot of stuff. I can produce, yeah, again, BPS spectrum. This is usually meant the same thing as Gukov homology. There is pretty much unique choice of what I mean by this, because 3D n equals 2 theory has 4 real supercharges. Only 2 of them are preserved by the boundary condition, and up to conjugation, there is essentially one choice, so that's not much of a difference. And as we discussed yesterday, we're going to encode much of it in a Q series. So that's my next goal, to tell you how, given this input data, to produce a Q series. And we'll see lots of magical things about it later. Any questions so far? Yeah. No. That's, yeah, so this is, yeah, it's a good question. It's a usual confusion that everyone working in 3D correspondence always has. So this question is totally normal, and it's actually good, because otherwise there could be lots of confusions. So 3D correspondence relates two sides. And it's even practitioners have to clarify on which side they are when we are in the middle of conversation. So it's always confusing. So this partition function that I'm going to describe is taking, yeah, so it's taking 3D n equals 2 theory, which is supersymmetric. So that's the TO from 3 side. And yeah, this side is supersymmetric. This side is topological. So there is also TQFT side. So this TQFT leaves or is defined on M3. This T of M3, 3D T of M3, is in the background of S1 cross a two-dimensional disk, because counting the operators on a boundary of such configuration where you have this 3D, 2D coupled system can result in this geometry. I can actually illustrate or comment on it in a second, so I'll come back to it. But the point is that space-time for this 3D theory is here, space-time for this theory is here. So if you think about it from six-dimensional picture, combining both, you would say that your five-brane theory, so six-dimensional 6D five-brane theory, leaves on product of the spaces S1 times D2 cross a 3 manifold. And yeah, if you sort of focus on first factor or couple of factors, you get supersymmetric description. If you focus on what happens on M3, you get a topological description. Another way to say it is that here we're using, I mean, in this 6D five-brane theory, this side is topologically twisted. So that's why it depends on metric on M3 only up to smooth transformations. But this side is non-topological. So they're actually not quite symmetric. And what I'm describing here is perspective from 3D n equals 2. If I were, so it's an interesting separate question, what happens on M3? So roughly speaking, this is this TQFT. Some of you were in the previous lecture asking questions about like Liouville or generalization to this VOAs, which are more exotic. So this is actually interesting because this is TQFT, which is basically, it's almost like Chern-Simons, but for complex gauge groups. So it's complex or analytically continued Chern-Simons. So this is roughly complex Chern-Simons theory. But now we understand this much better in terms of quantum groups at generic Q. So since I'm working with SL2, for me, this will be UQ SL2. But the important thing is that unlike WZW or Chern-Simons, here Q is not the root of unity. So not a root of 1. Yeah. So does it clarify the question? So yeah, this is basics of 3D correspondence. Maybe one more remark before I jump into the definition. So why this S1 cross D2 geometry appears since I went into this digression. So what we're considering, I'm going to redraw the same picture, is a system of 3D n equals to bulk with, on the boundary, we have 2D 0, 2 supersymmetry. And what we're trying to count is, in this BPS spectrum, what this Q cohomology counts is anything that can be found at a point on a boundary, but it can wander from the bulk, it could be object on a boundary. And usually when we have local operators and we want to count them, this counting can be expressed as some sort of partition function. So by state operator correspondence, it's usually the same as asking what are the states on a sphere that surrounds my local operators. But here, because this point, the way I'm drawing it, I hope you can visualize it, lives on a half space, so there is a boundary slicing it. What I actually have is this point is surrounded by a disk. So, and then radial quantization requires me to take the trace. So that basically, in radial quantization, it means that I have to take radial directions and close it up in a circle. So that's how we get, in this picture, the relevant partition function would be S1 cross 2 rather than S2 partition function. So if I were counting local operators in the bulk of 3D n equals 2, it would be S1 cross a 2 sphere. Here it's S1 cross a disk. And it still remembers about my boundary conditions. So in other words, this is the same as a solid torus. So I can draw a picture of a solid torus like this, such that inside the solid torus, we have 3D n equals 2, but on the boundary of solid torus, so boundary is still the same 2D 0-2 theory that we had originally. So just a different, so there are many different ways to think about this partition function or whatever we're gonna define. If this remark was helpful, that's good. If it wasn't helpful, just scratch it and I'll give you, again, mathematical definition in a second and that's gonna be fine. Yeah. So I'm going to erase these ingredients in terms of theories that we don't even know yet anyway, and replace them by a computational tool. So it's, as I mentioned last time, it's quite remarkable that in this case we have zillion, so this is supposed to be an illustration, that we have lots and lots of theories because there are lots and lots of graphs to play with, and again, this is tiny universe of something much, much bigger. Nevertheless, all of them are strongly coupled. We have no clue what these theories are, and yet we can compute this BPS spectrum quite explicitly. Just, again, think about analogy with harmonic oscillator. So we'll define these partition functions in the following way. So first, I'll call them z hat. This is for some historic reasons. For each such decorated graph gamma. So this will be function of Q, and it will involve remnants of some of these decorations that graph had. So I'll call this B. So this thing will be principal value integral over many, many variables, as many integration variables as vertices in a graph. And each one, so I'll call them, let's say, xi or xj. So here there will be product over I in vertices of the graph, dxj over 2 pi I xj. And each one will be integrated on a unit circle. Okay. So then we'll insert lots of stuff here. And the rest of the integrand, so it's going to be like a long formula, will also involve product of basic ingredient over vertices and edges. So for pairs of I and j, which belong to the set of edges, there will be also some kind of ingredient. And then we'll stick in one last thing. It's going to be theta function associated. So it will depend on all of the x's. It also depends on Q. And it will be a theta function associated to the quadratic form B that is basically defining the whole thing. So I had this adjacency matrix associated with the graph. And that's gonna, I mean, once we have quadratic form, you always should write a theta function or always should construct a lattice. Maybe you should jump immediately to constructing lattice VOA. It's also a good idea. It's not a joke, actually, in this case. But anyway, yeah, so that's gonna be ingredient here. And theta functions have characteristics, and this little b, which I put in red, is gonna be one of those characteristics. So to finish the definition, I have to tell you two things. I have to tell you what integrand, or other basic building block, will associate to vertex. And then just like in statistical models, when we take products over Boltzmann weights, we'll just take products over same thing for each vertex. And same analogous thing for edges. So I basically have to tell you what's the analog of Boltzmann weight for vertex or edge R. If you don't like my figurative speech about Boltzmann weights, think about Feynman diagrams where you have propagators and vertices. So I have to tell you what what is the rule for vertex and propagator, okay? So there are basic ingredients. And they're not so complicated. So for vertex, labeled by B, the rule is that so I told you that we have as many integration variables as vertices, so there is natural assignment of x's, xi, xj to our vertices labeled by I and j. And if you have one such vertex, its integration variable appears as part of the integrand, and there is some power of q, so there is this q which is now gonna play a major role. So this is x minus 1 over x squared. Now, edge, which we don't know, and think about this as some kind of 3D n equals 2 version of theory T of G, or T of SU2, or some kind of bifundamental matter. In any case, it should transform under gauge groups that sit on the right and on the left that edge connects. So it should be charged under fugacities, and this axis should be thought of as a gauge fugacity or holonomy for left and right gauge factor. So therefore, if you have an edge connecting vertices I and j, then the rule is that it should correspond to something that depends on xi and xj, and this is simply 1 over xi minus 1 over xi, xj minus 1 over xj. Okay. So that's it. So this finishes the definition. So yeah, that's all. So maybe one more thing is kind of aside. For now, assume this bilinear form, quadratic form B, to be negative definite, or you can actually relax this to say weakly negative definite. Think of it as a technical assumption. One of the reasons is that we want to get a Q series which has positive powers of Q, or at least goes into positive powers of Q, possibly indefinitely, but not the other way around, because again, if you think about exponent of Q is associated to the energy, then we want energy to be bounded from below. So it's best if we don't run into any kind of trouble. And the issue here is that if you think about what this complicated looking integral really is, it's a convolution of some rational function, which is basically product of such factors of over lots of xi variables with a theta function. So theta function is what do you think it is? It's sum over some lattice of many n's. I'm going to decode this in a second in a slightly different way. Q to some quadratic power associated with the inverse. So this is going to be minus n b n over 4 in my conventions, and then product over I, xi to the ni. So, I mean, any theta function is usually q to something quadratic and x to something linear in terms of summation over lattice element. And you see here in my definition, I put here a minus sign. So if I want positive powers of q, as we usually have in various partition functions and various modular forms and things like that, then B better have some negative definiteness. And this is what this small technical assumption is assuming for now. I'm going to relax it actually by the end of the talk and see what happens. Naively, something bad will happen, because if I, for example, try to do the opposite, if I ask B to be positive definite, then I'll have this expression with powers of q going to arbitrarily negative values. So it sounds pretty bad. So it sounds like I'll basically take my energy and put it upside down. So, but we'll come back to this question. It's going to be a lot of fun, in fact, in the end of the lecture. But for now, let's assume that that's the case. So far, so good? Yeah. Exactly. That's exactly how you should think about it. It's a partition function of a theory that we don't know. Yeah. Yes, but I'm not gonna tell you the intuition. I mean, there are several ways to arrive to it by now. Luckily, there are many derivations, and again, it fits in much larger subjects, which has to do with quantum groups and many other things. So there are several ways to derive it, actually, at this point. But I'm not going to tell you those. So I can give you some references, but yeah, I think it's because it's still not going to help. It will help for connection with other subjects, but it's not going to help to solve it's not a homework problem, but a serious problem of finding this class of theories. So the best I knew, I already told you. So these are, again, the best I know is that these are theories whose Lagrangian is not known at present. They look like Skirmy-type theories. They're close enough to be this bifundamental matter, but yeah, we don't know the Lagrangian. So it's very sad. And for mathematically minded or VOA or CFT minded audience, I'll have analogous problem. So this is like on QFT side, but there will be analogous problem once we go through some calculations. There will be analogous problem asking to find log VOAs for exactly the same data. So given a graph and all of this, there should be a log VOA. And this is something that Terry mentioned in his lectures, that we'll have some partial information about log VOA, for example, its characters, but reconstructing it is a non-trivial process. It's a little bit of an art. Yeah. It's a definition for the purpose of the present lecture. If I had another set of definitions, it would be consequence or computation or theorem, but at this point, it's my starting point for today's lecture. Because I'll have theorems based on this definition, and that's how mathematics functions. We define something and we derive something from whatever we started with. So, right, fair enough. Okay. Any other questions? Yeah. Hmm? Yeah, so integration over SU2s is in some sense, yeah, reflected in this measure. But there are similar factors actually arising from edges as well. So what's going to happen once you multiply this out, actually, this is a much longer way of writing it. I'll give you a slightly different presentation of the same expression in a second. But once you multiply it out, you can ask where same xi appears. It appears from this factor for each vertex, but also every edge, which is incident to that vertex, will contribute a denominator. So we'll actually have xi minus 1 over xi to the power 2 minus degree of that vertex I, product over i's. So all of this rational function could be written much more succinctly. Instead of using 2 lines here, I could have just said this, because it factorizes. I mean, there is no really interaction between xi and xj. So this is much more complicated than it really is. Yeah. There is no. These are some weird, yeah, so roughly what this wants to be is bifundamental matter, but it's not. So, I mean, yeah, so for whatever reason, yeah, with bifundamental matter will give you something else. Yeah. So you can construct many, you can construct actually many close cousins of this family of theories by replacing this with something Lagrangian that you know and love, and that's going to be fine. But it's not going to be, so that will work for purposes of constructing just partition functions of QFTs, but it will immediately violate all the questions why. So that's why I spent whole first lecture motivating that not only this is interesting and like in its own right, it actually connects to log CFTs, to this, to so many things, and all of those will fall apart if I replace this edge by something much more elementary. So, yeah. But I view this as a good thing because for connections to other subjects, we're forced to work with something non-Lagrangian, and this is cool. When we signed up for QFT course, we sort of sign up for learning or pushing frontiers of QFT. And we don't want to stay in Lagrangian frontiers. I mean, we want to go beyond perturbative. So. Okay, so far so good? All right, so then maybe, let's see, where is it? Oh, here it is. Right, so this definition, like I say, it's actually slightly more complicated than it needs to be. There are simpler ways to write it. You can think of this. So yeah, so this integral is not really much of an integral. Again, it's a convolution of a rational function. Here it is, product over all the vertices with theta function. So that's perfectly fine. And yesterday we discussed how some of the basic ingredients are arising. For instance, integral over x is trying to take gauge invariant operators and so on. You can actually connect it to what I was discussing yesterday. And you can basically do exactly that. So you can take this rational function, expand it out in x, multiply with this theta function, expand in x, and take a constant term. And then what you're going to be left with is not really an integral anymore, but summation over this integers n. So therefore, what I'm describing to you, so this thing, this sort of half-index partition function for graph type theories, which depends on only single variable q and, well, maybe this possible additional remnants of characteristics of theta functions, can be written as a lattice model on a graph. So think about, so now by taking this integral by residues or constant term, you can actually keep the summation but remove the integration. And it will allow you to think of it as sort of Ising model on graph that we had originally. But it's going to be different from the usual Ising model, and that's a kind of cool thing. So that's why you cannot easily, I mean, it's, even in lattice models, this is beyond something that's usually studied. Because Ising model has spin half, which takes two values, plus minus one. We know that Carroll or other Potts models have q-valued spins and so on. Here we'll see in a second that spins on our sides are infinite spins. So they'll take infinitely many values. So it's like infinite spin limit. So you could say, well, that's actually okay because XY model is basically a limit of infinite spin chain. But the reason XY model is pretty simple and boring is because we start with a spin model on a lattice and take spin to infinity while keeping nearest neighbors interactions. Another second feature that's new here from the lattice model perspective is that it's going to be not nearest neighbor interaction. It's going to be highly non-local. Every spin is going to interact with every other spin. So I don't know if I still have the graph. Basically, you'll have spins sitting at every vertex of the graph, and they'll be interacting one with another. For example, this one will be interacting with every other spin at the same strength of interaction very far from it. So this is very different from usual limits that people study in lattice models. So therefore, we'll have two things, infinite spin and and highly non-local interaction. This is pretty cool, and it's reflecting two things. It's reflecting, so I mentioned to you that in quantum group language, this is trying to compute some quantum group invariants associated with quantum group at generic Q. And you should think of this infinite spin as direct consequence of it, because when you work with quantum groups at roots of unity, values of your spin are basically bounded by that order of root of unity, by the level. So it provides a truncation on everything. That's what makes life very finite. That's why we love roots of unity, because everything sitting in a box. The moment you move away from roots of unity, your spins can be infinite, and that's actually what's reflected here. The non-locality is owing back to origin of this theory in 6 dimensions, which I mentioned is non-local QFT. The fact that we didn't have a Lagrangian in 6D, and the fact that this 6D theory is non-local is translating to very non-local interaction on the graph. So that's how conceptually these aspects are arising. So anyway, let me not go too much into conceptual discussion, but just try the latest model. It's actually pretty simple. So you have summation over the spins, so ni's, so there are integer values. I'll write prefactor in a second, and then there is q to the Hamiltonian for the spins, and Hamiltonian is actually very simple. So Hamiltonian is basically minus a half of sum over I and j, and then you have an I and j, and then B inverse ij. Okay, so B is our adjacency matrix of a graph, and B is pretty sparse because it only essentially for each given vertex, it has non-zero entries when vertex I is connected to fellows j, okay? But once you take the inverse, it's a very standard fact in matrices, in algebra, that inverse of a sparse matrix is actually maximally dense matrix. So that's what controls this interactions. So, and each ni is an integer, and the only thing I have to tell you is what this prefactor is. This is maybe not terribly important, but it's also not very hard to see. So I'm going to help this definition with another one by introducing a function f. So for each vertex I, we'll define the following set of values, fi, comma n, labeled by vertex and integer n, same as over there, as, so this is a definition, as a symmetric expansion of the following thing. I'll take z minus 1 over z to the power 2 minus degree of I. That's exactly the expression that appears here when you take the product over everything. And you first take expansion at z equals 0, and then symmetrize it by adding to it analogous thing, z minus 1 over z 2 minus degree of I, expansion at z equals infinity. What this says in plain English is basically that if I have, for example, if my 2 minus degree is positive, I just expand it out. You can use Mathematica command expand. Well, you can use actually the same command even if this degree is negative, but then what I try to emphasize here is that I want to have this running in negative powers of z as well as in positive powers of z. That's all. So it's like kind of symmetric expansion going both ways. But intuitively, that could have been clearer. I'm just trying to make it very precise. And then what I'm going to do is I'll stick in here a factor product over I in vertices of my graph, decorated graph, of f, I, and I. Okay? So that's going to be sort of prefactored. So, and that's it. With this definition, you have yet another way of writing. So our claim is that it's a small lemma that this definition and this definition give you exactly the same thing. In fact, I try to explain what the proof is or where it comes from. The proof is just take this integral by residues or constant term, and you're gonna end up with a sum, which is what's written here. So this integral is not really an integral. I mean, this is integral if you like localization, partition functions, but it's what it's really is, it's like a spin model on a graph. So, okay. All right, so this is what it looks like. Here I can show you Mathematica code, how it works. So you can find this code in many places. Let's see what I should erase. I don't think we need this anymore. So because it's not an integral, and or even if it was, you can take it by residues, or you can use directly this summation. It's a simple combinatorial calculation, so it's no harder than Ising model, which is 100 years old. So it can be computed extremely fast, and that's where you can find various versions of the code that computed. So I'll give you one on my Celtic side. So then there is, so this is Mathematica realization. Then there is also a Python version. So for those of you who prefer Python, here is another version. So it operates on much smaller set of graphs, but also does additional things. So their functionality actually are not quite the same. So they're somewhat complementary. But I'll walk you through this calculation if you want to do it in practice. So first half of this Mathematica file is input of the graph. You can see I chose a graph with 4 vertices. It's very simple. So then it computes various preliminaries. For example, looks at eigenvalues. This may be important if we care if it's definite, positive, negative, and so on. So this is not really a calculation of the Q series yet. And then it goes roughly here, it starts computing BPS spectrum. As you can see, there are no integrals. It's basically summations. You can see some of the expressions from the board, and here it is. So it's extremely short. In fact, I know when it was first written, nobody tried to optimize the code. I'm sure you guys can write it in 10 lines. So this is a simple hackathon challenge to write this whole thing in 10 lines. I'm pretty sure it's possible. It's not rocket science. It's extremely simple. I mean, the definition is on the board. And this is what comes out. So we see expression that is very similar to expressions, for example, like for harmonic oscillator, the one that I was showing you before. So it has form q to some fractional power, and then multiplied by a series with integer powers, integer coefficients. That's pretty cool because, again, this integer coefficients are counting something. So these are counting this BPS states or dimension of Gukov homology. And yeah, that's what it looks like. So promised use this form, that's what you get for any essentially 3D n equals 2 strongly coupled theory defined in this way. But there is something to note about it. So I'm gonna copy this answer and save it here. And I'm actually gonna change the graph. So I'll do it in real time here. So for instance, I'll add another vertex. So I'll connect 4th vertex to yet another one, create a 5th one, and I'll change some of the decorations here and redo the calculation. So evaluation, I'm not sure if, yeah. Let's quit kernel, recompute everything. Yeah, so first of all, maybe let's go back up. So you can see that I completely changed my theory. So it used to be SU2 to the 4th theory because there were 4 nodes and lots of matter. Now it's SU2 to the 5, so it's a completely different theory. I have different gauge group, different everything. So my Chern-Simons levels, which are precisely these numbers, are completely different. Nevertheless, what's interesting is that the answer is still the same. So those of you sitting close enough can see that this expression and this expression exactly agree. So this is sort of interesting magical property that we got the same answer. So we can ask, is this an accident or is there a system to it? But actually, that's why this class of theories connects to so many other fields, because if I started choosing, for example, fundamental matter or something else for this edge, I would not have this crucial property. So what is this property? And I'll list you now lots of properties, basically why this is exciting. I already mentioned some of them earlier. So simple, or maybe not so simple theorem is, so this goes back to our work with Pei, Putrov, and Waffa, 2017 or so, where we prove several statements. So first of all, we show that this half index for graph type theories is convergent Q-series inside the unit disk. So this is an easy fact that you can quickly check just by ratio test and things like that. That's not too hard. But more interesting property is the one I just demonstrated for you, that it's invariant under some set of moves. So these are very interesting set of S-duality-like moves which relate different theories. Because we don't know these theories, we don't have their Lagrangian description, I cannot tell you that this is analog of Seiberg duality or given Kutasov duality in 3 dimensions. These are new dualities in 3D which relate different theories. But it's not a magic, or it was kind of expected the way the story proceeded, because we want to associate these theories to 3 manifolds. And sometimes there are, not sometimes, but there are infinitely many ways to construct the same 3 manifold. And all these infinitely many ways are related by only few moves, which are analogs of Reidemeister moves. If you know, for example, a little bit of knot theory, then there could be many diagrammatic representations of the same knot, but they're all related by only 2 or 3 moves. And same thing is true here. There are just a couple of moves that relate infinite set of different ways of building the same 3 manifold. So to people who work in 3D correspondence, this is not magic, but it is magic if you just put your 3-dimensional QFT hat and ask, okay, do I know these dualities? And the answer is no. We don't know these theories. We don't know what these dualities are. These are just truly new QFT dualities. But anyway, at the level of this BPS spectrum, we can see that it's invariant under what's called Kirby moves. And what are these Kirby moves? For instance, if you have some piece of your graph, gamma, which looks roughly like this, it has a vertex labeled by some A or B, and it's connected to other vertices. This is fairly generic configuration. Then what you can do, you can replace it in the same connected structure to the rest of the graph by B plus minus 1 vertex at the cost of creating yet another one with weights plus minus 1. And that's exactly what I did a moment ago for you. And then there is another analogous move like this, which takes two such guys labeled by B1, B2, connected by the edge. If they're sitting somewhere in the middle of the graph, then you can have yet another Kirby move, which does similar thing, creates a new vertex and a couple of new edges. So you don't change the rest of the graph, but here you change B1 to plus minus 1, B2 to B2 plus minus 1, and introduce yet another guy. And then there are two more moves. I'm not going to write them, but again, you can find them in some of the references I mentioned. So we have a huge universe of 3D n equals 2 strongly coupled theories, which we don't know. We have dualities relating them, which again, we don't know. So I could have easily stated here a cheap problem. Maybe I'll put it in writing. Describe this duality. So this is, again, not a homework, that's an actual problem. So describe physically these new dualities. Relating such QFTs. This, of course, is not an independent thing because you have to answer probably previous problem before you can tackle this one, but maybe not. I don't know. I would expect that that's more natural course of action to understand that. Okay? Yeah. Yes, so that's actually, there were questions, how do we know these expressions and so on. That's exactly how they're understood. So from that point of view, that's how this was derived in the first place, and that's also how this gives a conjecture that there are such theories related by dualities, but it's, yeah, physically it doesn't prove that yeah, anything about these theories. That would be too weak. That would be too poor. So if we didn't have this whole 3D correspondence, I would not bet my money on this. I mean, it still could have a chance, just because BPS spectra, sometimes one can be lucky. But here we have a lot more. So if you know that it comes from 6D, if you have really good control and pretty sure you're not missing a billion flat connections and all the generalized symmetries we talked about, then this 3D correspondence predicts that there should be equivalence of such theories. Yes, that's right. So that's a very good question. Just on basis of BPS spectrum, I would be very shy to make this conjecture. It would require additional luck. So, yeah. Okay. So maybe at this point I should tell you something else. So there are lots of interesting properties of these theories and lots of things that one needs to understand or study further. This Mathematica notebook, if you look at this website, it's called Plumbed. So the reason is that this whole class is called Plumbed. What does it mean? So a little bit of three-manifold geography. So simplest class of three manifolds that you may want to introduce are called Breeze-Korn spheres. So usually they're labeled by three coprime integers. I'll call them P1, P2, P3. And that's how this class is denoted, sigma P1, P2, P3. So it's defined in a very simple way. You basically take P1, P2, P3. You define it by taking a set of equations x to the P1 plus y to the P2 plus z to the p3 equals 0. So that's a hypersurface in 3 complex dimensional space. And you intersect this with a large 5 sphere, which could be a set of points, absolute value of x squared plus absolute value of y squared plus absolute value of z squared equals 1 or 50. So this is 5-dimensional. This is codimension 2 locus, and it cuts out for you a 3-manifold, which, if P1, P2, P3 are relatively prime, is a homology sphere. So it contains Poincare sphere and lots of other spheres. So these are spheres of Mr. Brieskorn. This is a pretty cool class, and in fact, the manifold that I showed you here is realization of, in our example, it's this 3-manifold is sigma 237. Okay, so it's one of the simplest. So you might have heard of Seifert manifolds. These are manifolds which are basically fibrations of a circle over 2-dimensional surface, possibly with lots of singular fibers. So S1 fibrations over something 2-dimensional. Yeah, I'm not gonna maybe write it. So they contain Brieskorn spheres, so the Venn diagram is like this, but it's still pretty small class. I mean, these are extremely special, at least in my point of view. So then goes this much larger class of plumbed 3 manifolds. That's the one we're discussing. This is the one associated to graphs. And this is the largest class I know that if you try to extend, you basically get all most general 3 manifolds. So therefore, I chose for you something that's not too trivial and something that can, is only one step away from generalization. So those of you who are interested can explore those generalizations. That's also fun and doable. Yeah? Huh? No. That's why this is important generalization, but again, much of what I'm describing can be generalized to hyperbolic ones. In particular, you can compute this series and so on and so forth. So I wasn't joking when I said that it's not a bad idea to, once you have a quadratic form, construct a lattice VOA. So here is a nice point where I can connect to discussion that Terry had in previous lecture. So there is a sequence of logarithmic algebras related in various ways to some non-logarithmic algebras that you may know, such as W algebra or lattice VOA. So in classical non-logarithmic algebras, you might have heard of Felder complexes, or sometimes if you have a screening operator, it's a good idea to think about cohomology of screening operator. But many log VOAs can be constructed as kernels of not cohomology, but just by taking a kernel of a screening operator. For example, that's how triplet arises from lattice VOA. And for SL2, triplet is labeled by 2 integers, and the family that is most studied, I think that's what Terry mentioned, is usually labeled by 1, p. So you can think of it as a logarithmic minimal model, which usual minimal model wouldn't make sense for these values, but it would be something like 1, p minimal model, and you can generalize it to PQ minimal model. And I don't want to use Q because Q for me is quantum or Q series. So sitting in here, this has SU2 automorphisms. or SL2 automorphisms. If you take invariant part, you'll get singlet VOA, so it means singlet with respect to this automorphism. And both of these algebras have the central charge of 1 comma p minimal model, which is the usual 13 minus 6 p plus 1 over p. Okay. So for instance, if I didn't lie in the algebra, for p equals 2, we should get minus 2, which is the same as symplectic fermions, but more interesting cases are p greater than 2. And yeah, you know probably something about W algebra. So anyway, this is all very cool. Theorem. So this goes back. Yeah, maybe I should not do the attribution because there are many different ways to prove it. Yeah, if I have time, I'll make comments later. That what we computed, this object here in particular, on the one on the slide, if I take this Brious-Korn sphere, sigma p1, p2, p3, then what I'm going to get is a character. So all of them, there are characters of 1 comma p singlet log VOA. And one can say precisely what characters, how different values of p's, and in case if there are this additional labels b would translate into the left hand, into the right hand side. But I'll just tell you part of this dictionary. In particular, what is the value of p? So p is very easy. It's going to be p1, p2, p3. Okay, so it's just a product of these guys. So when many years ago I showed this fact in the audience of Mike Friedman, so he got super excited because so this happens to be character of log VOA for p equals 42, and he said, oh, 42 is the answer to the meaning of life and Hitchhiker's Guide to the Galaxy. So here 42 arises for a very trivial reason because it's 2 times 3 times 7. So, and of course you can have any other value, so, but it's just a coincidence that this is used often as a simple example, and there are many good things about it. Okay. So this, of course, is not a coincidence. From physics considerations, you can argue, and so we did many years ago, that this should always be true. So in fact, conjecture, which is essentially what's called 3D modularity conjecture, that for all such decorated graphs gamma, and more generally for all theories of this type that, as Cyril proposed, we generalize further to hyperbolic manifolds, this calculation is going to be a character of some logarithmic VOA, and there is some partial understanding of what this logarithmic VOA is. For example, if you have a graph which has some number of high valency vertices, high valency means valency greater than 2. For instance, you don't consider these points, they're not terribly important. You don't consider these points, which are valency 2, but you focus on vertices which are valency 3 or higher. So then you can construct this log VOA. So the candidate for it is mutual intersection of kernels of screening operators, as many as you have high valency vertices. So we have a recent paper with Boris Fengin, Miranda Cheng, and others, where some of the ingredients here are fleshed out, but of course a lot more work needs to be done. So this is a conjecture that, I mean, Terry was asking for kind of new factory of potential log VOAs in a way. I mean, not only we need examples, we need some machinery that allows us to shed light on the properties, because even defining this analog of modular tensor category that Terry would probably call log MTC is a subtle business. So we want to know how many, so how many projectives we need to include and what exactly should be the size of S and T matrices and so on and so forth. That actually can be read off from this physics construction. So basically the bottom line here is that there is this picture of 3D n equals 2 theory in a bulk with 2D02 boundary conditions, and that's producing for you this whole factory of new interesting log VOAs, which can be viewed as intersections of these kernels. Again, in traditional non-logarithmic VOA, we usually take cohomology, but if you just take kernels, do not mod out by images, then that's a candidate for such, for many log VOAs. And I promised you that there will be a problem. So obvious problem now is construct this log VOAs. I mean, make this more explicit. So luckily, it's not just, I mean, this picture, partly physical, partly mathematical, provides for you like a direction where to go. So an obvious problem is to mathematically complete this mathematically. So mathematically define this log VOAs. So at least some steps are already there. So that's a good news. You're not starting totally in a vacuum. Okay. So another theorem that I already mentioned earlier, that's in recent work with Mrunmei Jagadale, is that this definition is fairly straightforward, and again, it can be generalized in various ways, and you can compute it. So the good thing about it is that it's very computable, it's very fast, it's actually as best as you could hope for. So from the growth of the coefficients here, so theorem says that these coefficients are supposed to grow as real part of this exponential of 2 pi square root 1/6 C effective times n plus 2 pi I and some rational number. So in particular, you can extract C effective from this growth, and it may or may not be real numbers, so or a positive number. So it's very common in non-unitary theories that it can be negative or sometimes even possibly complex, if it's even more exotic. So therefore, from this growth, you already have not only, again, picture of what it should roughly be like, but you can start extracting, and you know its characters, but you can start extracting data such as central charge or effective central charge and various other things. So one thing that is also expected to hold in absolutely great generality is the following curious fact, which has been checked in every example and leads to the following conjecture, which you should try to prove or disprove, that this object for any such T of M3 of this particular kind that we're discussing, but also more generally, can be written as a multisum over D1 through D, I don't know, sub n of q to something quadratic. So you'll have here an expression of the form n c times n plus maybe linear part. And here you'll have q Pahimers, q d1 through q d sub n. So in 80s, in fact, going back to late 70s, in the study of relation between conformal field theory and integrable quantum field theory, this is physics origin of Kazhdan-Lustig correspondence, which relates vertex algebras and quantum groups. This was super popular. So this sort of expression for characters of conformal field theories is called fermionic form. So fermionic form of VOA characters. And this is something that's, again, back in late 80s and early 90s, mostly in 80s, was heavily explored by many people, starting with Zamolodchikovs. They basically kind of introduced the subject. It relates to thermodynamic beta ansatz, again, many, many other things. But I think Barry McCoy is the one who coined this term fermionic forms. So Barry McCoy and many of his collaborators and other people pursued this further. I mean, this list is really long. And the important part of this relation, or what's good about it, is that the matrix C here that enters, as you can see, denominators are pretty much universal. I mean, they just Q Pahimers for pretty much any version of the sum. But interesting information sits in this quadratic form in the numerator. So therefore, you should think of this formula being essentially controlled by this matrix C. So that's the essential part. And in that story of fermionic forms, integral quantum field theories, which are deformations of CFTs, this matrix C played a very important role. It connects to R matrices and so on. In particular, its size tells you how many primaries you have, and so on and so forth. It's a beautiful, rich story. I hope you have seen this expression in previous lectures. So recently, from a completely different point of view, this sort of expression was rediscovered as quiver form. So in a study of Donaldson-Thomas invariants, Donaldson-Thomas invariants also naturally arise in this form. And that's not a coincidence for us, because remember, this whole setup started life as 5 branes embedded in some M-theory setup and so on and so forth. And if you look at it from this perspective of the M-theory target space, these BPS states that I'm describing to you are exactly some kinds of Donaldson-Thomas invariants. So therefore, it's not really a coincidence that the same structure governs this part of the story from sort of world volume perspective, and there is also a enumerative target space perspective on the same object, and it connects these two subjects. So the reason I'm saying this conjecture or stating it here is that just like the effective central charge, it can be useful because in those old days, Barry McCoy and many others essentially made a dictionary how to reconstruct CFT from this matrix C and vice versa. So they try to develop this dictionary connecting the matrix C. So now all we have to do, I mean, this is very useful. So my point is that if you manage to write, for instance, this expression in such fermionic form, you already get a lot of information about CFT. So Terry was emphasizing in his talk that 99% of the time we want to be very pedestrian, working with combinatorial data. And that's exactly what these characters are. They're very pedestrian, combinatorial, simple. There is nothing categorical here. We want to upgrade this to information about CFT itself. And this fermionic form can be actually very useful for that matter. So I mean, I would argue that that's one of the best starting points to think in terms of this matrix C. Okay. Now, for us, this is something that still needs some work. So conjecture based on all this M-theory enumerative stuff tells you that such form should exist. but I don't know what it is. In fact, even for this simple example, it's slightly non-trivial job to reconstruct what this matrix C is given the input data. So what was the input data? The input data was a decorated graph, or equivalently, matrix B. So therefore, my next problem for you, and again, this is a problem not of the homework type. Problem of a homework type is try to compute more examples and play with them. So again, I even gave you Mathematica code, so you can sort of do it using computer algebra systems. But the actual problem, which would be worth a very, very good paper, is work out the map. Find the map that takes a matrix B, which was part of our input data, so that's what specified the graph, into this quiver matrix or fermionic form matrix, C. Okay. It's easy to check that C is not equal to B. I mean, they're called by different letters, so they cannot be the same. But jokes aside, in this example, yes, you can, for example, go to this matrix. This is my B. You can verify that, no, that's not the correct one for this character. I mean, it has to be something else. And nobody knows this map. But what's interesting is that we have a computational device. So I mean, I don't know direct combinatorial map how to construct one symmetric matrix out of another symmetric matrix. But I have a way, first of all, to compute this BPS Q series, and then read off the matrix C. So this procedure is indirect, but it's very computable. I mean, in every particular example, it doesn't take long to figure it out. So therefore, one way to approach this is to either train a neural net to do this and basically do some self-play, construct lots of synthetic data and figure out what the combinatorial map is, or have a couple of graduate students to team up and outperform the neural net in this problem. Either way, I think it's going to be a very good problem to work on. Okay. Any questions? Yeah. What is? Yeah. Can you say louder? This or the N? Oh, sorry. D. Yeah. Thank you. Thanks for correcting me. This is station was D. Yeah. So this is D, C. Yeah. Thank you. Yeah. That makes sense. Yeah. D's and D's. Linear in D. Yeah. No, linear part, I mean, there is also, there could be a minus sign to some power and linear part, but this is much smaller data than the matrix C. So in this old study of integrable QFTs, matrix C contains more information. So it's, yeah. Yeah, you also need the linear part. Yeah. Yeah, well, yeah, that should determine C plus, so I'll write like this, plus the linear part, right? So because there is a map, so you can compute it. But so I would be tempted to say, yes, it should fix it uniquely. However, I don't know if Marcus told you that these quivers have lots of equivalences. So there are various mutations and so on. So actually, there are many different quivers which represent the same form. So it's actually, I mean, this set of matrices is up to some equivalence relation. But also, remember I told you that this set of matrices B is not quite unique. It's up to equivalence relations, namely Kirby moves. So what makes this map, or finding this map, slightly difficult is that it's not going to be unique. It's going to be unique on equivalence classes under these moves and under these moves on this side. So probably one strategy could be to work out a map from a representative here to a representative here. But again, one has to keep in mind these relations. Yeah, so that's sometimes present. Analog of those X got integrated for us. So for if you work with manifold which has a boundary, there will be X's. These are the same X's that were part of the integrand in our setup. But the final expression has no X's. So if you have a closed manifold. So basically, yeah. Yeah, so what I'm saying is that the setup that's relevant to 3D correspondence is basically doesn't have any additional access. So they could have been, for instance, if I were working with manifolds that have 3 manifolds which have boundaries, it would be literally like his. So there will be Q's and X's and everything like that. But once you work with a closed manifold, there is only one variable left. It's the Q. Yeah. Well, basically, X's are analogs of Keller parameters, but once you work, so if manifold had a boundary, there would be analogs, but once you work on a closed manifold, there are no X's anymore, and yeah. Another role of Keller parameters could be introduced. I do everything for SL2. I emphasize throughout the lectures I worked with rank 1. If you did rank n and try to ask what is the rank dependence, that would be another place for Keller parameters. But yeah, and this is something one can study, but I'm not discussing it here. So maybe I'll mention one more. So I gave you lots of facts and problems. So maybe just one last thing about this connection to logarithmic vertex algebras. There is actually a lot more to be said. So this is an interesting phenomenon that's these days is called going to the other side. So we were discussing this 3D correspondence that relates something, some kind of TQFT on M3 and 3D n equals 2 theory, which is in the setup that I keep redrawing. So this is 3D n equals 2 theory, T of M3, and so on and so forth. And everything starts in 6 dimensions where both are part of the same space-time. We have a product of this geometry, and it's 6-dimensional. But 6-dimensional theory has no parity symmetry. So it's good to talk about symmetries. I've already done it a number of times. So if I apply parity transformation, parity means reversing orientation of one of the directions in 6 dimensions, my theory is not going to be invariant. I mean, the reason is very simple, because it's a 6D 0, 2 theory, and 0 is not equal to 2. So therefore, if I reverse, then it cannot have this invariance. So if I change orientation on M3, so that's an interesting operation that topologists actually care a lot about. So in topology, low-dimensional topology, this is very important. I have to do something else, otherwise it's not going to be a symmetry of my theory. But it's easy to see that flipping the sign orientation on M3 can be compensated by orientation reversal here in this other 3-dimensional setup of 3D correspondence. So this change can be made a symmetry if I do a parity operation here. Parity, okay? or orientation reversal, because then I can think of it as changing orientation here and here in 2 directions, and that's basically a rotation in 6D, so that's actually a symmetry. That's good. That's not a big deal. But this operation does something very funny. So at the level of 3D n equals 2 theory, any parity operation would keep the theory pretty much the same, but if we have Chern-Simons levels, it would flip the signs. So for instance, here at the level of this 3D n equals 2 theory, for the matrix B, it would take it and replace by the inverse. So remember, I cared about some definiteness, so it would actually do exactly a legal thing. It would take it and try to reverse, and from the viewpoint of this VOA or Q series, it would take my energy. So when I write this sum over n, Q to the n plus delta, or En plus delta, I don't know, something like this, it would take my energy and reverse it. So my Q series would try to become Q inverse series. So that sounds pretty bad, but we know from physics that it always produces a Q series with positive powers of Q. So something interesting is going on here. And this operation is actually highly non-trivial at the level of this 2D02 boundary condition. Because, again, 0 and 2 are not equal. So what it takes, so there is some boundary condition here, some B, which is 2D02 boundary condition. And it takes this to some dual boundary condition by the following operation. It, roughly speaking, takes the left sector, which was non-supersymmetric, that's the 0, and supersymmetrizes it so that it's n equals 2, and vice versa. It takes the right sector, which was n equals 2 super-Virasoro representation, and desupersymmetrizes it. So it's a highly non-trivial operation at the level of these boundary conditions. So this is yet another new duality. That's a very cool thing. And until recently, we didn't have a very good handle on how to work with this. But in particular, natural question is, how do we compute this Q cohomology or BPS spectrum in such a setting? I mean, it sounds really funny. But more recently, the progress in this direction came from resurgent analysis, which is something that Lotte has mentioned. And very roughly, or actually maybe, yeah. So what it tries to do, it takes this BPS spectrum and tries to replace Q by 1 over Q, but in such a way that the result is still written in terms of Q. And making sense of this operation was required in many different fields in mathematics, and from this picture also in physics as well. So for instance, when we think about Kazhdan-Lusztig correspondence, that was briefly mentioned, those of you who know what Kazhdan-Lusztig correspondence is, the usual proofs of Kazhdan-Lusztig were for only one sign of the level. So for them, it was very crucial that the positive and negative zone, as they called it, are very, very asymmetric. So things are very nice in one sign, and if you try to flip it, basically the hell breaks loose, and usual proofs don't apply. So if we discuss things like singlet and triplet logarithmic VOAs, an actual question is, what are their analogs on the wrong side of the level? So this is actually not worked out at present, and there are many works or candidates that are being proposed, for example, by Dennis Gates-Guri and his students, involving chiral Heike algebras and other things, but they're so unexplicit that we cannot even compute the characters of those beasts. So we don't know how to define them and so on and so forth. So what this machinery does for you, it allows to produce, this resurgent analysis that Lotte briefly mentioned, it allows you to produce characters of not only new logarithmic VOAs, this is cool and exciting and so on, but it allows you for the first time to access the other side. Not the other side in the sense of left and right, but the other side in the sense of going to negative versus positive Kazhdan-Lusztig zone, which is, again, until so far was approached with very esoteric tools like semi-infinite cohomology and so on. That's what Terry called the higher level of, higher form of life. So this allows you to access that with more combinatorial tools, something where we want to be 99% of the time. So therefore, my last and maybe natural homework at this point is to understand this singlet and triplet and maybe many other log VOAs on the other side, on the other side of the skazhdan-lustig zone. So I want to thank you for your attention, and since I'm the last speaker, I also want to thank all the organizers, Catherine, Fabrizio, then Masahito. Yes, I'm probably forgetting others, but yeah, so thank you for putting this workshop together. Right, so no, not really. So the paper I mentioned, which has mapping tori in a title, so those have cycles. Yeah. So that's also good reference for that. But they're more interesting. I mean, you're absolutely right that once you start having cycles, what is a cycle? Cycle is, yeah, it means that your graph is not simply connected. If you translate this back to the world of three manifolds, it means that manifolds start having first Betti number, which is non-zero. So that's actually more fun, yeah. Because that's where all these generalized symmetries come to life. I mean, so many things become more exciting. Um, Well, yes and no. It depends. If you work with some of the restrictions, for example, if you assume that determinant of this matrix B is non-zero, then the answer is yes. But in this last part, I try to indicate that it's actually fun, and that's where current research is relaxing those conditions. So we actually can relax the condition that determinant of B is equal to zero. So it's fun to consider graph like this, single point, and B equals zero, right? So that's not going to be a rational homology sphere. In fact, this is S1 cross S2, and that's a fun, simple example. Yes. Yes, and that's actually another good question. It's being observed that some set of graphs, for example, this one I don't know. I mean, this is slightly more exotic with B equals zero, but suppose that B is non-zero. Then this is a class of length spaces, and they produce characters of totally normal non-logarithmic VOAs. And one can work out, in this case, this Gukov homology. That's the same as boundary algebra, and it's indeed non-logarithmic. So there are, and then there are several other examples that are of this type, but I don't think anybody tried to classify. So it's funny that in this large world of logarithmic stuff, sometimes we have sprinkled in, for very special choices of this input data, non-logarithmic things. I guess it would probably fit with your general picture, right? That log is more generic, but why this occurs and at what particular values, to me, this is not systematized. Um, no, in this case, it was identified, but in other cases, not. That's right. So in other cases, we have a smoking gun that character looks like that. The next step is to actually work out the algebra and see that, yeah, whether it's rhythmic or rational. Yeah. That has not. That's another natural problem. So in Terry's name, there is another problem for you to work out when rationality occurs in this logarithmic universe. Well, many things are wrong because mathematically it's defined. So Yeah, I mean, as a gauge theory, you would write path integral dA e to the, I don't know, h bar Chern-Simons, because Q is complex, h bar is complex. Let's keep it just any complex value. But you would immediately ask the question, I mean, what does it mean at any level of rigor, even physics-wise? Because the difference between compact gauge group and non-compact is that um, non-compact group such as SL2C has infinity, so you can run off to infinity. And yeah, whenever we have moduli spaces, for example, in Gromov-Witten theory or in any other moduli problem like Donaldson-Thomas, we don't like non-compact moduli spaces. We have to say what happens there. And therefore, I mean, this is very important for non-perturbative definition of the theory. Question is, do we add some divisor here at infinity that will be compactification divisor? And if so, it may introduce new critical points. So they may not only be critical points of original Chern-Simons, which are complex flat connections, but something else that sits here. And yeah, recently now we see that, oh yes, there are, by embedding this whole story in this M-theory picture or quantum groups at generic Q, there are indeed, I mean, it's not just complex Chern-Simons. So physics statement is that non-perturbative completion of complex Chern-Simons is something strictly bigger. So that's what I meant by the fact that it's better understood. And but original theory, I mean, it only makes sense as perturbative theory. So well, one major problem in that in this area, if you so this goes back. So established could be at physical level of rigor or mathematically. Physical level of rigor, I would say the answer is yes. And I mean, everything I told you can be easily generalized to pretty much any manifold, so we can compute everything, BPS spectrum, all of that for hyperbolic manifolds and so on. Mathematically, we need one ingredient. So it's mathematically, almost everything is a theorem, but there is one important piece missing, which is, so this is yet another problem. So to make it absolutely rigorous for all manifolds, I mean, it already is done for many hyperbolic ones, but important class involves zero surgeries. So this may sound too technical, but this is a very special class of manifolds on knots and links, which participate in many important conjectures in low-dimensional topology, including even smooth Poincare conjecture in dimension 4. And it's probably not surprising that these are harder, much harder examples than even generic hyperbolic manifolds. So that's what's missing to make it fully mathematically rigorous. So there are lots of examples for example, this paper with Fagin, Miranda Chang, and others. Sang-Yuk may help me with other paper. I mean, there are probably other papers. No, that's more recent. Uh, so the one we had with Tobias also has some examples, right? I believe. Yeah. So there are several papers that we wrote, and probably other people. Yeah, we can. I mean, ask us, and we'll give you references. So there are lots of examples, and it's. I mean, this map is again at the technical level. I showed you the Mathematica code. It wasn't a joke. I mean, you can do it in 10 lines. So in Python, you can probably code 2-page or like I don't know 50 lines of code which does neural net analysis of this map. But I mean, so it's actually quite serious that this can be done and analyzed. But Uh, well, it's understood on each side separately. It's not, again, very complicated on this side. It's extremely simple. And on this side, it's reasonably simple. But they don't align. So that's what makes it funny. So the map between equivalences is not one-to-one, or it's not even aligned in any easy way, as far as I know. I don't know if you agree or disagree. At least to me, it's not clear. So it looks like we're working with sets of different equivalences. And that's, to me, what makes it slightly non-trivial.